Okay, so here we have the next question on the menu, and it is asking us, or is presenting the situation where we have a diatomic gas originally with a volume of 2 cubic meters, a pressure of 200 kilopascals, and a temperature of 50 degrees Celsius. The gas expands isobarically to a volume of 3 cubic meters. Now it is asking us what is the work done on the gas by the process, the final temperature, and the heat transfer of this gas as this process occurs. So the first thing that we need to address here is what does it mean by isobarically? Okay, so isobaric expansion, what's going on here is that the pressure is constant as the volume increases. Now, assuming that there is no additional material added to it, no additional gas added, the temperature has to increase to keep the pressure constant. Because as things get more hot, their pressure increases, right? Because gases expand when they are at higher temperatures. So the hotter that it gets, the more outwards pressure it's going to be. But if the volume increases, the increase in volume must be happening in parallel with an increase in temperature in order to keep the pressure the same. So the volume increases and temperature has to increase. Those two things have to happen at the same time for the pressure to stay constant, because increasing the volume reduces pressure, but the temperature increases the pressure. So you're kind of balancing those two things at the same time. Okay, so let's actually write down our givens. So our volume 1, or our VI, for initial volume and our final volume. So our initial volume is 2 cubic meters. Our final volume is 3 cubic meters. That is actually fairly large. 1 cubic meter is about the size of, or about the volume of a human, to be honest. You could hide in a 1 cubic meter box if you wanted to. So these are fairly large volumes. The temperature initially is equal to 50 degrees Celsius, but we want to convert this to Kelvin. So 50 plus 273 Kelvin. So 273 plus 50 is 323 degrees Kelvin. And our final temperature, we don't really know that, so we'll probably need to find that eventually. And our pressure is 200 kilopascals. Or another way that we can say that is 200 times 10 to the 3 pascals, just to have everything in base SI, which could be useful. Now, the equation that we want to use here is this equation right here for the work done. So work done is represented with W for work, makes sense, and is going to be the pressure times the change in volume. So V1 minus V2. Now the reason why we're doing V1 minus V2 is because normally when you do change in things, you're doing the final minus the initial. The reason why we're doing it this way is because the question, now this is where precision of language gets very important. The question is saying, what is the work done on the gas? It's not the work done by the gas, because the gas would be doing work to be increasing its volume and its temperature. But since it's the work done on the gas, we're actually doing negative work, okay? So we're going to expect a negative result like the magnitude would be the same doing either way, but we want to set it up this way so that our sign is going to be negative, because there's negative work done on the gas, positive work done by the gas. Okay, so subbing in our numbers, we get 200 times 10 to the 3 pascals multiplied by 2 cubic meters minus 3 cubic meters. So we could just write that as 2 minus 3, that's just negative 1, so it'll just be negative 200 times 1,000 joules, or 200 kilojoules. That could be another way to say it, but yeah, this would be the work done on the gas. Not sure why they mentioned by the gas though. Okay, interesting. Now the second part of the question is asking us, what is the final temperature? Now to find the temperature, we want to use this relationship, because the volume and the temperature are very closely related. Like I mentioned before, if the volume is increasing, that decreases the pressure, and the temperature has to increase to keep the pressure constant, otherwise it's not isobaric, which is one of the conditions of this question. Okay, so for part B, we know that our relationship is going to be our final temp over our initial temperature. The ratio between our final and initial temperature has to be the same as the ratio between our final volume and our initial volume. So if we're trying to solve for our final temperature, we got to do our final volume divided by initial volume multiplied by initial temperature. And final volume, that is 3 cubic meters divided by 2 cubic meters multiplied by 323 kelvins. 323 kelvins. So 323 times 1.5, another way of saying 3 divided by 2, 484.5 kelvins. Okay, so that shall be our final temperature of the gas upon its isobaric expansion. Cool, and yeah, probably exactly came to precisely the same answer here. And the last question is, what is the heat transfer into the gas? So the heat transfer is going to be the same as the work that we're doing, because like all the work that is done on the gas is becoming the heat. As we're increasing the volume, any energy that we're adding to it is just going to it's just going to be heat. So all the heat transfer is going to be the same as the work done here. So it's going to follow the same procedure as calculating it with this equation. So that shall give us our the amount of heat energy that is put into the gas. Now, if it told us, and I guess we also know the final and initial temperatures. So if we wanted to, we could calculate like the some of the heat properties of the gas itself, and maybe use that to help us identify it. But that is not part of the procedure, so we don't really need to worry about that, or not a part of the question, so we don't need to worry about that. And yeah, so this solution is good.